All right. Okay. Hello and welcome everyone to this particular podcast. Today we have with us Dr. Hanie Sedghi. She is a senior research scientist at Google Brain working on research problems related to understanding and improving deep learning techniques. She works on designing algorithms with theoretical guarantees such that they can work efficiently in real world scenarios. Prior to that, she was a research scientist at Allen AI, and before that, she was a postdoctoral fellow at UC Irvine. She graduated from USC with a PhD with minors in mathematics. Thanks a lot for being here, Dr. Sedghi, and I am looking forward to this conversation.
Thanks. Thank you for having me. Excited to have this chat with you.
All right. So, in order to understand more about your research interests, can you tell us a bit about what kind of projects you are working at currently at Google Brain, and what is the impact that you are trying to create using those research problems?
Sure. So I've been working on understanding and improving deep learning for the last, give or take, 7 years. And I believe like my approach has really been to be in the intersection of theory and practice and like remove the gap or reduce the gap as much as possible. And I think there's been great progress in deep learning, but and our understanding has been really lagging behind our practical success, and this growing gap really makes some obstacle to go beyond this current use of deep learning and like extend its use to other domains in a reliable way, because we have less information available to us. And I believe bridging this gap would help us extend the current use of deep learning to new domains in a reliable way. And I've been leading this team called Deep Phenomena at Google Brain, which is a group of people with similar interests and agenda working together. And my main focus has been generalization, and even more recently, out of distribution generalization, and also try to understand these large models that we use in practice, and try to investigate what's missing, how can we improve them, and so on.
Right. Yeah, that seems interesting. And so before we go into the depth of your research problems specific, can you tell us a bit about your entry point? Like, how did you get started? How did you get intrigued about deep learning research? And in specific to understanding the theory behind, like not just applied areas of deep learning research, but understanding the fundamentals and theory behind the deep learning.
Sure. So my background is machine learning theory, and at the time deep learning really started to come back, I was working on non-convex optimization methods. And of course, it's really intriguing that like training a deep neural network is a highly non-convex problem. And so, of course, I got intrigued about it, and I'm really interested in solving puzzles. So that was and I realized that a lot of people are thinking about deep learning, and I was like, okay, what is this new thing that everyone is interested in? And then, of course, the type of questions I asked was really inspired by the type of angle that I have on problems, and this has grown over the years. An interesting story was that my first workshop paper in deep learning was at NeurIPS 2014 deep learning workshop, and I had this work on provable methods for training neural networks with sparse connectivity. And a lot of people stopped and asked, what does provable mean? And then I had a follow-up work submitted to NeurIPS, which essentially extend this to shallow neural networks, not just as far as like general thing. And the status story was that one of the feedbacks, like one of the reviews we got, was that we don't need theory in deep learning. I asked AC that for sake of community, reject this paper, which at the time I was a junior researcher, hit me hard. But I'm glad that as a field, we've come this long way that now we have like deep learning theory tracks. And also the gap between theory and practice is really shrinking, which is great.
Yeah. And this brings me to a question: is before we need to get into the details of few of the terms, is how does like you said, most of the people, this is only some time back that even reviewers rejected this particular idea of focusing on theory of deep learning. So in a very bird's view angle, how can you explain that? How does the understanding of theory of these machine learning techniques help us in whatsoever sense, be it application related or in general from a developer's perspective, or just from a theory like developing much more efficient algorithms? if you were to explain me or someone who doesn't know about the theory, who just understands, okay, it's just an import function in Python to just do these kind of things, how do you explain that?
So first, I want to mention that like theory means a broad range of things as long as we really try to understand something, whether it's complete phenomenal investigation or like complete theoretical, like complete mathematical proofs. I call these all theory as long as we're really trying to understand what's going on. And the real bird's view, if we understand the different pieces of what is making a machine work, then we could, and what parts are missing, then it would make it much easier to make that better, um, and like have more handles on it.
I see. I see. Interesting. And also one thing, like tying two of the points that you mentioned is you really like solving puzzles that you said along these deep learning techniques. And like you said, there are multiple components that makes a deep learning model. So in terms of understanding the theory, do you have any kind of still and puzzling thing that you find interesting that really works, but you don't have a very clear explanation that, hey, I don't know how this works, but this just works perfectly well in a deep learning model? Do you have any kind of puzzling thing that over the time you have realized you do not have a theoretical proof or a guarantee that you have for it, but surprisingly in most of the cases that we use deep learning models, it just works perfectly fine? Do you have any kind of special component of a deep learning model?
So I really look at interplay between data, training algorithm, and architecture. I don't really look at them in isolation, but I think the fact that deep learning generalizes this well is something that is still intriguing for a lot of people. And as we make the problems more and more complex, of course, we're finding the places where we have failure modes of deep learning, but still this this generalization in terms of pattern recognition part is an interesting thing, and like trying to understand um, what really makes things work. So for example, early on we were thinking about we really need to implement some biases in our architectures. However, these days we're seeing that if you add a lot of data, the model is able, and if model has enough capacity, it's able to capture those biases. So I think as a field we keep moving forward and we see interesting things that we didn't think would happen.
Interesting. And I have one other question that I normally tend to ask most of the speakers, and I think this is kind of interesting to ask you is what motivates you for these projects? Do the like exploration of what is the theoretical background to a particular working that really intrigues you to solve a particular problem, or is it the application that, okay, if I solve this theoretical problem, then it can actually aid a particular application? In your choice of working on projects, what motivates you more, the application behind it or the theory exploration that you can do for those problems?
So I really don't focus on a really specific application. I try to be application agnostic and work on methods that work for a wide range of applications. But what really motivates me is that, first of all, what question I find interesting, because if as a researcher we don't find something interesting, then it's like we wouldn't really make progress on it. And the second
Yeah,
thing is that if I solve this problem, how much it's going to help the community or people. And so that's what really motivates me. Um, yeah.
I
Then the
see. I
tools are
see.
secondary. Like once I figure, okay, this is the problem I'm interested in, then I'll figure out how to solve it. But I think the part that is the exciting part is that like this problem that is interesting for me and like I want to solve it.
Right. And jumping onto a few of the specific questions that are related to more of your research works and that I did some homework and digging on is, can you explain the terms over parameterizations and generalization in deep learning models? Like these are the terms I think most of the people who only work on the backbone of deep learning models really understand and really play along with, but not a lot of people from the applied domains really work on. But can you explain more, like what do these mean and what are the significance of understanding these two terms in deep learning models?
Sure. So let me start with the over-parameterization. So essentially, in classical setting, we think about this um, overfitting phenomena, meaning that as you keep getting better and better on your learning your training data, then your test data starts to getting better, but then it starts to get worse because you're getting to a memorization regime. then as you keep increasing the capacity of your model, what happens is that then like this, there's this, what we call it, this double descent phenomena, that the test was getting worse, but then now it starts getting better. And this happens after you completely fit your training data, which we call interpolation regime, where you have like 100% accuracy on training. And beyond this point is where we call it over-parameterization, where you have fit the training data, but as you keep training and as you keep increasing your capacity, your test accuracy is getting better, or your test error is getting um, smaller. So this is what we mean by over-parameterization. And like generalization, essentially, it's a really big, like really broad term, but in very basic ML is that you train your model on training data. It doesn't see test data. If it works well on training data and if it works well on test data, this is what we call generalization. So it generalizes from whatever it learned from training data to some test data that it hasn't seen. And then the distribution can be the same, which is the in-domain case, or it can be different, which we call it out-of-distribution generalization.
I see. I see. And in this particular scenario, because from what I naively understand is over-parameterization could be really bad in terms of like doing over-parameterization. Like, are there any benefits to doing that, or is it bad? Because I think we are just surpassing the boundary of overfitting a model, right? So we are going into that territory. Are there any benefits? Because there are lots of, I think, discussions that say over-parameterization can lead to generalizations or vice versa. Like, do you have any insights on that? Like, is it true? Is it false? Or is it something that really needs to be understood on a subjective basis?
Right. So, yeah, I can tell you about it. So, there is this understanding that we have as a community because of the long list of papers that work on it, that essentially we are doing some implicit regularization. So, SGD is doing some implicit regularization when we are training it on the empirical risk. And so some sort of norm is being implicitly regularized and made smaller. When you over-parameterize, you're essentially making your network bigger, so the solution space become bigger. And now it's possible to find smaller norm solutions, whatever that norm is. So because of that, and this essentially means better generalization because you're minimizing that norm that really relates to generalization. So the advantage of over-parameterization, as I talked about it, is better generalization. It makes your optimization easier because the loss landscape becomes nicer. And also it gives us a more robust solution. The downside or disadvantage is that you have higher training time, you need a lot more memory, and also it takes longer to do the inference.
I see. I see. I see. And so, would you suggest that doing over parameterization would be on a subject to subject basis, right? So it would be application dependent. So in certain cases, you would want to use a big model or a large parameter model, even if the data set is small, or maybe I would say generalizability is achieved, but would you in what cases would you say over parameterization would have any negative effects, as in it hurts the idea of using the deep learning model on that application?
I think you really need to think about your restrictions that you have either on training time or memory or inference time. If you have a really small memory and you really have no time, then it takes time to train that over parameterized model, so you can't really use that. So really need to think about your budget.
Mm-hmm. And this brings me to a recent work that I think you published on. I'm not sure if it's a conference paper or an archive submission, but it really digs into the idea of using scale and transfer learning techniques and how it affects the upstream tasks versus downstream tasks and the relations between them. And one of the observations that these applications show is that if you are trying to improve your upstream task performances, you might actually saturate the performance on downstream tasks. So can you tell us a bit about the intuition that we learn from those experiments in this particular work, and what does it mean in terms of using transfer learning? What things people can derive or learn from that particular research study when they are using transfer learning? And because I think like most of the people are trying to hint towards transfer learning as a potential way forward, right? Like they are trying to focus more on developing better pre-trained models and then using them rather than just training everything from scratch every time, doing the reinventing the wheel or models or something like that. So can you share some insights on intuition behind that, and what can people learn from that study?
Sure. So this is a recent work called Exploring the Limits of Large Scale Pre-training. And essentially the reason we looked into that is that we have this current impressive success in deep learning that is like CLIP, that essentially we use really big models trained on a lot of data, and it seems it works well for downstream tasks. And so it seems like that we are, as a community, we think that, okay, let's just keep increasing the scale, whether it's model size, data size, and compute, and get better pre-training performance, then it's just going to translate to better downstream performance. So this is what we question. Does this mean that as I let me just keep scaling up, it's just going to give me a really good checkpoint, a pre-trained model, and it's going to solve all my problems? So that's why we were like, is this really the case? And the reason we looked into this was that there were some earlier analysis that said, yeah, this is the case. However, they were looking at really limited case of hyperparameter tuning and limited accuracy range. So we had access to about 4,800 experiments that our different colleagues had trained these models, and then we analyzed them and say, okay, is this the case? And for this, we looked into two big upstream data, which is JFD and also ImageNet 21K, that is like available for everyone, and looked at more than 20 downstream tasks and a variety of tasks like ImageNet, which is people usually use, meta dataset, VTAB, medical imaging, VOLS dataset. So we tried whatever we found, we looked at it. And as you said, one thing we saw is that you do get saturation. So this plot that we kept looking at was for different models, what is the downstream versus upstream performance that we could see, and then we feed a mathematical model to it. But what we see across the board, across all these variety of downstream, is that as you keep increasing your upstream performance by increasing the scale, you hit a saturation point. And even if your accuracy reaches 100% on upstream, your downstream would stop well below that. And our mathematical model can exactly give you, okay, for this specific downstream, where would be the saturation point? So I think this is really important for us as a community, that we can't just scale up everything and say, okay, you're done. This is Oracle model that I found, and this is going to solve all your downstream tasks. And in addition to that, we poked into why this happens, and we designed some experiments to look at different layers. And I'm not going to get into like all the nitty gritty stuff, but essentially, one takeaway we had is that if you want to get better saturation point, you really want to look into having more diverse data in your upstream. So that's one thing. But even like for us, for practitioners, a couple of takeaways that we have, giving like all these investigations in the paper, which I wouldn't get into all of them, is that a lot of times practitioners, when they want to think about downstream performance, they have ImageNet or C410 or 100 and say, okay, I scaling up C400 or ImageNet is getting better, so this is a good model. But what we showed extensively in the paper is that different downstreams have different reactions to this. I mean, they all plateau or saturate, but some of them saturate much earlier than that. So even if we want to find a checkpoint that is helpful, we need to look at really diverse set of downstreams. So that's one thing. And the other thing is that, yeah, of course, the scaling up will have to saturation. If I want to get into more details, is that what it means for a community going forward is, for many of these downstreams that are not well correlated with upstream, really top layers of these pre-trained networks are the ones that are useless for downstream, because as we showed in our earlier works, lower layers are learning general features and top layers are learning features that are really specific to upstream. So what this means for us as a community is that we could change the way we fine tune, or we could essentially discard these layers and do something else so that we could better leverage this data in the downstream. And of course, as I mentioned earlier, we really need to think about having diverse data for our upstream and also probe different downstream tasks when we are doing this. So yeah, I'm really excited about this result, and thank you
Yeah,
for
yeah,
asking
no,
about it.
yeah, no, definitely. I mean, it's a very the thing that I liked about that particular study is you have a very nice way of, at least these, I think, are much more of an intuition. Most of the researchers that they try to understand, but this is much more like an empirical study that actually showcases the actual behind the scenes of what's happening and why things could saturate versus why things they cannot. And I'm curious about one question. I think you touched very briefly on that, is the idea, like, is there a way? I think these results definitely tell us why the performances on downstream tasks might not improve versus how they would saturate. But is there a way for us to learn more about the correlations between the upstream and downstream tasks? Meaning, in certain cases, these kind of scaling up can actually help, versus in certain cases, like you said, you also tried downstream tasks on medical images where initially the pre training was done on natural images. So, is there a way for us to quantify that correlation that, hey, if it is not correlated by a certain amount, we shouldn't be using these things? But if it is, then hey, we can just use that for better performances. And we are under the assumption that hey, computation resources and time are not a factor, and those things. So I'm curious if there was any kind of observations you saw over there on those notes.
Sure. So one thing we did was, in addition to looking at these experiments that other people had done, we did some controlled experiments where we specifically controlled for model size, data size, and compute, and we see the similar pattern in terms of saturation and also in terms of the function that we see, which is good news. It means that we did this so others don't need to do it. In
Yeah.
addition, this mathematical model that we've proposed, we do analyze it in terms of robustness to number of samples in the paper, and we see that you really don't need to have this giant number of samples in terms of trained networks to really fit our mathematical model, which is essentially a power law that shows nonlinearity. And so let's say you have a small number of networks that you've trained, you could use this model that we've proposed to be able to predict when does your downstream saturate, and that tells you, okay, and and essentially what does it mean is that it predicts when does downstream, like what is the saturation value of your downstream as a function of your upstream. And so
Mm.
essentially you would know how much you need to spend money on to get your upstream to that value, and then that would mean, okay, that would be where your downstream is saturating. So essentially, like, you have a handle on this function, and you would have a handle of how much budget you have, and based on that you could essentially decide how much more you want to push, as opposed to, okay, let's just push it to see what happens. So you really now like have opened the box and you see what's going on. And so that essentially helps you, like, that functional formula, it helps you understand, like, where does this downstream, specific downstream that you're playing with, sit. Another thing I wanted to mention is that, like, so for everyone, like for everyone, we all understand that, okay, medical imaging is very different from cats and dogs. We're very different from natural images. So we understand that it's going to saturate fast. However, an additional thing that we found was interesting was that it's not just the shape of the image that we as humans would understand. There is these data sets such as pets and cars that they also saturate really fast. So the distribution of samples in this space of images is also something that is really important. And that's what we would only be able to see when we did this analysis. So what I'm saying is that humans are not enough to understand if what is this correlation. Yeah, for medical images it's easy, but when you get into space of natural images, having this tool that we propose essentially helps you figure out what would be specific to this downstream.
Yeah, no, I completely agree to the last point. I think one of the fundamental differences between natural images and medical images, because most of my projects are on medical images, so I lately understand this. It's the kind of data distributions that create a lot of problems. The first problem is, of course, small data sets. I mean, most of the community cries about that. So there's nothing we can do, as in it's much of more of a physical effort. But in terms of the diversity, for natural images, we could have multiple classes. I mean, thousands of classes. But for medical images, it's hard to create those naturally. We can create those artificially. So I think, yeah, I totally agree. There is a kind of a much more distinctive difference between doing these experiments on natural images versus medical ones. But this brings me to an interesting question. Is maybe this is a maybe very naive question, and this relates to a work that you earlier published on transfer learning and understanding the behind the scenes of transfer learning. Is I wanted to clarify, or maybe just ask this question: is most of the people have this concern that if we are using transfer learning on large scale data sets where the pre-training happens on a very huge data set versus the fine-tuning happens on a very smaller data set, then transfer learning cannot have real much benefits because the model is huge and the fine-tuning doesn't really help because it's a small data set, and hence the fine-tuning efforts are very small. Versus there is also a concern that you cannot use small models because transfer learning is not really provable in terms of small models. We are not trying to incorporate the benefits of transfer learning in small models. So I wanted to understand, because this feels like an intuition, but we don't have a theoretical understanding that, hey, if this is actually true. And I'm curious if you have come across some works, or maybe have you explored in one of your works that talks to more about these things, but much more in a guaranteed fashion that, hey, this is actually true or false.
Right. So yeah, speaking of that, our earlier work on understand on what is being transferred in transfer learning, we found a couple of really interesting things. There, we look at models that are pre-trained on ImageNet and look at like natural, like medical images, and also different variation of natural images. And one thing that we see is in class of functions, pre-training is essentially helping in the sense that it is putting your model in a good basin in lost landscape, so that essentially it helps the optimization getting better when we are doing fine tuning. So that's where it helps. Of course, as you keep increasing the size of your target or downstream task, then our colleagues have shown that the effect of transfer learning is gradually diminishes. So if you have enough data, you really don't need to pre-train. But back to the cases that we don't have enough data. So I think I wouldn't discard transfer learning because, as we also showed in our paper, it really helps the network understand these lower level features that we know that would like help capture the edges and like texture and so on. So that would be beneficial. The part that we want to make sure is that, as we also explained in the paper, the top layers are really specific to the task that it's pre-trained to, and they may or may not be useful for downstream tasks. So one thing we could do is to focus on fine-tuning those layers, and also like in few shot setting, when we discard the head and we put a new head on it, we do essentially train the head. So I wouldn't completely dismiss transfer learning. I think it helps bias the model in a way that helps optimization. However, we should always keep pushing on having a really good fine-tuned model with as much diverse data as possible, in addition to working on improving our fine-tuning methods so that we could essentially help the network get closer to what we really intended for, as opposed to just staying in a place that is more specialized toward the data set that it was pre-trained on. So as a community, we still have work to do, which is exciting.
Yeah, definitely. This is actually very interesting, because when I was trying to do kind of a homework behind asking questions for you, is these kind of papers actually, or publications, I would say, really help us understand the getting a confidence on these models or these techniques, I would say, rather. And for, like, surprisingly enough, I think one of the last speakers that I had, she's also from Google Brain, and she worked on the understanding of transformer models versus CNNs, and similar questions is arise. And like you said, this community has to do a lot of work. And this brings me to a question as to, we understand these kind of, like, this is, I think, very initial works on understanding and proving theoretical guarantees. In terms of longer context, where do you see, as in what kind of benefits that you can ideally imagine or dream of while people are working on theory of machine learning techniques? What kind of benefits we can, as the overall community can get? Like, what do you envision this domain of research to be like?
Right. So I think we've been working on showing the community what are the things that are missing and where we are failing. So, for example, we looked into failure modes of out of distribution generalization, and out of distribution generalization is essentially what we need because you always train on some data that's going to change some way or the other when you test it. So, I think like understanding deep learning essentially helps us see our failure modes and where we're missing, but also give us direction, like this work that I mentioned, that these are the things that we're missing. So let's take a step back and look where we're going and make sure that we take care of the failure modes, but we also improve our method. So one example that I have, which is one of my favorite papers, is that back when I started at Brain. So that was the time that ResNets were like really big thing, and if you wanted to regularize them, you had this giant 4-dimensional tensor, and good luck taking SPD on that. So there was people would get really stuck on that. Like when people were using GANs, they wanted to regularize them or they wanted to solve inverse problems, and this regularization was something that was missing. So with my colleagues, we did some mathematical analysis of CNNs, and because of the shape of convolution function, we could actually simplify this to a problem which is essentially 2 lines of Python code, and that's it. It gives you all the singular values, and now you could regularize. And even at Google's scale, this made a huge difference of being able to take those SPDs and regularize versus not doing that. And that essentially enabled a lot of follow-up works, a lot of places that where people were stuck in improving their models or getting better performance or faster performance. That essentially opened the gate to a lot of enabling people to do a lot of follow-up work, which was really exciting. So I think that's another aspect that these investigations would essentially help us, and also helping us going beyond just pattern recognition and do more reasoning. And like, can we probe, first of all, how much network is reasoning and memorize versus memorizing, but also can we enable the network to do that? Can we add these capabilities to our network? So, and that's something that I'm really excited about.
Nice, nice. Yeah, no, that is very interesting. And I'm curious, have you had an exploration of comparing vision transformers versus convolutions? Let's say ResNet. I think ResNet is kind of a benchmark, but we can pick up anyone's. I'm curious if you had any kind of observations or understandings behind the working of vision transformers. I think it came out of Google research sometime back, like very recently. I'm curious because the reason I asked this question is these results were published on a huge data set that not a lot of people have the opportunity to work on or at least try those things. So it's hard to compare apple to apple. But I'm curious, have you had the chance or at least some kind of observation from others' work is how like can we rely on vision transformers? Is it something a paradigm shift, or is it something just parallel to ResNet? Can they really be replacing convolutions, or are they just an alternative thing that people can try on? And again, this question comes from a theoretical understanding, of course. It could be just a luck
Yeah.
that the vision transformers are working well on ImageNet dataset. But do we have any kind of theoretical understanding behind the working?
So that's a really good question. And I think we have not converged as a community on yes or no, in the sense that, so there is this recent work from my colleagues in Brain that they compare they compare them at the representation level, and it seems like okay, representation seems to be similar. However, there is another work from a group of folks that look on theorem proving, and they see that they are doing like essentially the seek-to-seek models are really doing a good job compared to ResNets. So, I'm aware of some ongoing work on really trying to look into these two class of models. So I think that's something that that I don't have a definite answer yet, and I'm excited that people are working on this. And I think it's um, good that like this line of transformers is really doing a lot of great improvement in terms of different applications.
Right. And in terms of, I think we also touched, I think you mentioned few of the limitations that deep learning currently has, as in not from a theory perspective, but the overall topic. But we have local versus extreme generalizations. And this is a known fact that deep learning doesn't generalize as well as humans do on any kind of decision-making process.
Of course.
But do you like, is there a relation between causal reasoning, between causal is in any way causal reasoning related to generalization? And if it is, can we understand how? I know this is a very open-ended question because again, the idea of causal reasoning is not very well technically defined, but it's an active area of interest. A lot of people try to understand. I'm curious from a theoretical like person who tries to understand things from a fundamental level. Is there a way, like, do we actually see any kind of traces that we can learn about causal reasoning of a model in future, of course?
I think that's a really good question. Of course, causal reasoning is also a form of a generalization. So essentially, if we're thinking like this, the really small notion of generalization that I talked about, which is catch the pattern on training data and using on test data, when we do causal reasoning, is the hope is to capture this causal relationship that is leading to this. So, and even if you think about reasoning as a general, you're essentially learning a specific function and you're generalizing your class function. So everything is generalization essentially. And I think as we are able to go beyond pattern recognition to capturing different functions and also like different causal relationship is where we're actually moving forward in extending the use of deep learning and machine learning as a whole to more complicated tasks and more exciting tasks and getting close to um, what we think like humans are doing, which is a philosophical thing by itself. But
Yeah.
um, and even like speaking of humans, I think one other area that I think is very interesting is that sometimes we don't think about it as much is curriculum learning. Even as humans, we have a sequence of things that we are exposed to so that we learn. And another thing that I'm thinking about in terms of when we have these giant models is that like the way that we are showing the data to the model could also play a role, and that could be something that would help us to learn more sophisticated functions and go beyond pattern recognition.
Yeah, yeah, I really like that idea. Yeah, definitely. And I'll choose this topic to segue to a slightly different topic that is outside related to your research topic and much more focusing on you as a researcher. Like most of the people who are listening to this podcast are mostly masters or graduate students or people who are generally interested in the research aspect of machine learning. I wanted to ask is you have spent a great deal of time as a student who is working on academic projects, the drill of being a PhD student, postdoctoral student who is working on projects, improving performances, publishing work, and the whole drill. I wanted to learn like what kind of differences do you see in like being a researcher in academia as a student or postdoctoral fellow versus being in a big industry who works on scale, as in what kind of things have you learned the way about research in computer science while you were a student versus academia? What kind of challenges that you saw that were interesting and that made you learn new things about research?
So I think the time that I was a student was a little bit different era compared to now, which is a good thing because I think right now there's so many podcasts and a lot of blogs and like a lot of online resources that like you see the world as is if you try. Earlier there was definitely the community was smaller and Twitter wasn't the thing, so you wouldn't go write about okay this is my new paper so people would know. I remember we would when we had a paper, we would just send it to as many professors that we had. Like, could you give me a feedback? So it was a different era, but I'm glad that as a community we've grown this much. I think um, as a student, there is, especially if you're not, if like you're not part of a like giant lab that has like I don't know 30 students or a university that has so many people in machine learning, is that sometimes you realize that okay your resources are limited. You really need to focus on something that you could do um, alone with your advisor versus now I feel I can really think bigger because I have a team of people. I have so many collaborators and there's so many people excited to working together. So I could really um, broaden the horizon. So I think that's one thing. But one thing that definitely helps you during your PhD process is that you really learn to, because your resources are limited, you learn to prioritize. Okay, what is the most important or coolest problem that I want to solve, and I want, and you become independent. You are like, okay, this is my research agenda. I really need to get it to finish line, which is my PhD thesis. Um, and of course, you learn to grow a thick skin because there's so many challenges, but that all those personality traits come to help you when you get into the bigger world. And life never gets easier, but it just gets more complicated or exciting or whatever we call it. So all those personality traits and all those essentially persistence that you learn during your PhD comes to your help. Um, and I think, like, as a PhD student, what I suggest people do is definitely learn the foundations, learn the basics, because the type of problems you work during your PhD and after your PhD might slightly change. But if you have the tools, if you know the foundation, and also like train yourself to do critical thinking in addition to have an open mind, that's something that would serve you along the way.
Right, right. Yeah, no, I take all of these advices very nicely. But just to comment on the first thing, like, do you like you started off by saying like initially when we didn't have that much amount of social media and people were just in the initial stages for machine learning. But an honest comment on that is like nowadays it's like an overwhelming response. Like every day you wake up, there people are publishing. Do you feel overwhelmed by keeping up with the progress in these fields? Like let's say even if you pick up any kind of basic computer vision domain or medical imaging, language processing, don't you feel a bit overwhelmed? Okay, I just need to read papers. Like this was initially my thought when I started in my undergrad. This was initial stage, and I was just being a naive, interested person in research. I felt okay, I can cope up, but nowadays it's just too hard to keep following even one person's work. So, do you also see it the same way, or do you have any kind of techniques that has helped you to at least I would say narrow down these bombardment of research works on archive?
That's a great way to put it. And I definitely acknowledge that it can be overwhelming. And I think FOMO is a real thing in our field because everyone is publishing a lot of things, and like field is moving forward really fast. And that is the way I cope with it, is like think about priorities, and like what makes sense to me, and and really acknowledge that, okay, as a human being, there's this much hours in the day, and I really need to take care of my mental health. So there should be a balance. Either we call it work-life balance or balance between different aspects of your life. And then I said, okay, it's okay. I don't need to know everything. And there are ways we could catch up with things, but not like read all the papers. Um, so even like although Twitter can be overwhelming, but also like it can give you like I really like it that recently, instead of people just saying I'm excited to share this paper, here's the link, go read it, they give you like a snippet of, okay, these are the main questions that we thought about, and this is the main finding. So in that sense it helps. But yeah, we did the FOMO is real, and we really need to prioritize and be okay with letting go of some things and not be expert in everything.
Yeah, yeah, that makes
It also
sense.
makes it exciting because once you talk to others that like they're specialists in something else, then you can have some discussion and like, okay, what is new in your field? And so be okay with that, and be okay with not knowing everything.
That makes sense. That makes sense. And one other question I wanted to ask is like because you have been on both the sides of research now, being a student versus now a successful researcher at Google. So, in terms of your, if you were to reflect back, and I think you would have struggled with defining your thesis, as in like what do you want to work on, what really interests you versus what you can actually do so that you can thrive into the research world. If you look back and if you were to advise someone, what do you really count for a good thesis? As in like how would you advise someone that you can say that, hey, at least if you have this many check marks, then that actually counts for a good thesis. And we are not being a very optimistic that, hey, just work on something that interests you. That's a very vague definition. But would you
Yes.
have any three or four things that you would advise a PhD student to consider so that he or she can have a good thesis direction?
Yeah, I think one of the favorite things that I have, and I'm quoting my friend Percy Leung, is that if you see everyone is running, following it, well, maybe that's not a good idea. I really like the way he puts it. Um, yeah, I think I want to say that there's so many low hanging fruits, but who cares if you write like 40 papers of low hanging fruits? If you really want to see if you've done a really good work, is did you take a step back and look at what people are doing and maybe propose a new angle or propose a new idea or even question, hey, this everyone is saying this, but maybe this is wrong. So those are my favorite theses. And I think in order to do that, it would be really good to have community of um, people who are more senior than you, and like you don't need to meet with them every week, but like get feedback from people, and also be keep an open mind, not think about, okay, this person is the best person, so I'm just going to follow what they're saying. Just keep an open mind, look at what other people are saying. Of course, your interest makes the space smaller, but in there it's like, what are the type of questions that people are not asking? What is the direction that I can come in? Where does my strengths help me? And also, I'll always look out for opportunities to learn new things. And I think one advice that I have, which I can't emphasize it enough, is that have mentors. Go talk to people who say, okay, this is my research agenda. This is what I'm thinking about. What is your feedback? Even if it's just a 30-minute chat, that would definitely be helpful. And don't shy away from asking people questions. I think a lot of PhD students, and myself included for a while, is like, you're like, okay, this person is so senior. How do I approach them? Just approach them. What's the worst thing that's going to happen? So definitely ask for feedback, and also keep an open mind, and also don't look for low hanging fruits. Um, and another thing that I want to mention is that definitely work on having this capability that if you have an idea, you could verify it, even if it's for something small, even if the model that you're looking at is small. Um, just get in there, try out ideas, think about things. If it's you're improving, try to do things yourself. Just as you were mentioning, there's so many papers coming out. If you just read too many papers, then you're paralyzed. You're like, okay, because you can't follow everything. So there, you need to really have some time schedule for, okay, let's take a step back. Let's think about problem myself. What does my voice say? How do I think about this?
Right. Yeah. Yeah. No, I can completely relate to this, and yeah, I can understand the depth behind these advices. So yeah, this is very useful, and this is something I have realized for my projects also, and this was along the lines of discussing with my other friends, other people that I normally talk to, and there is a major misconception that most of the people when they get into the PhD program is they're trying to invent something, but it doesn't have to be always like like reinventing the whole wheel, thinking out of the box, but it's like
Exactly.
understanding it's more of understanding the research problem and the techniques. And one thing that I think I wrote it down few time back is like make like compiling a model and running the model is the least thing you need to do as a CS research student, because that's what my basic understanding was, that majority of the time I would be just writing code, programming, and writing deep learning models. But I think that's something that what happens before training the model and after training the model that really accounts for the research. And I think that's where the learning happens as a PhD student. So yeah, it's something that what you said about persistence, I think that relates best into these two buckets. So yeah, this makes a lot of sense. And
Yeah, and I
just
think one last
so
thing I wanted to mention is talking about persistence and resilience. That's really important. And PhD time, grad school time there's a time that there's a lot of stresses, there's a lot of unknowns. So really know that you're not alone if you're struggling with it, and also get help in that sense as well. Mental health is really important, and we don't talk about it enough, but that's something that we really need to take care of ourselves, um, and definitely get help with that. However, kind of help makes sense for someone. So I think that's another thing that I want.
yeah, no, definitely, that's a very important point. I really love that. And just one last question before we end off is taking one other step back, as in like moving even from the research domain, is do you have any piece of advice for people? Because this question I do get when I was in my masters, and people would reach out of these podcasts and comments is they are in the domain of, they are exploring deep learning, they are learning about deep learning, that what deep learning stands for, what machine learning can achieve. They are interested by it, intrigued by it, but they are confused, as in like do they really want to make them as a career, or maybe dwell themselves into the research domain. They are mostly, I think even I was along those lines, I was pretty much scared that hey, I won't be able to keep up with these many programming and mathematical challenges. Do you have any piece of advice who are in that stage, they are trying to explore the I would say the creamy applications of deep learning. They're intrigued by it, but they are pretty much confused if deep learning is something that they are really interested. Do you have any piece of advice along the lines when you decided to pursue deep learning as a serious research topic? Do you have any advice for those people?
Right. I think that's a good question. Are we talking about people who are going to do PhD, or are we thinking about people who wants to go to the industry of deep learning, which is implementing it for different companies?
I think
Because
we can
those are two
segue into
different
that.
types.
Yeah, I think we can segue into that. But I think these are the people who recently discovered that they are maybe in the sophomores or freshman year of the college. They discovered, hey, this is something interesting that you can part of as a computer science student, and they are not really sure if like. Again, that would be a segue of part two question, meaning if they want to go into the industry and hence develop their career, or go into the industry and hence develop their career, which would be, I think, a different question. But this really relates to the people who have just discovered deep learning.
Right. I think so. For me, my taking a lot of steps back before even I got into deep learning, what I was excited about was solving puzzles. And I think, like, so as I was mentioning, my background is ML theory. I was doing optimization, convex optimization in high dimensional space, then non-convex optimization. Then I got into deep learning. I think really finding what makes sense to you, and along this path, of course, there's been so many subfields that I was like, this is not for me. I'm not interested. Really thinking about what makes sense to you. And also, I think right now there's no lack of having, even like in sophomore days, there's so many professors in universities say, hey, I want to get a project to see how does this feel, to try it for yourself, and also but ask other people. I mean, I do a lot of mentoring, and sometimes I realize when someone asks me, what does research entail? They want to get into research, and then they ask me, what does research entail? And then they're like, oh my God, you write this much and you'll have deadlines and you'll have to wait for it. Oh, that doesn't sound exciting. So, really, like when you hear something that it seems shiny and nice, get into the details. Is this for you or not? And there's so many opportunities to try things out, like get internship at industry, or getting internship in academia. See what makes sense to you, because there's a lot of opportunities out there, and just uh, finding out what makes sense to you and what is exciting, not on paper or on social media, but actually what does it mean day to day if I'm doing this, if I'm investigating this. I think that's really helps in making a decision for each person.
Yeah. I completely second that and resonate that. I love that advice. But yeah, I think that's all I had for this particular podcast. And I'll be linking few of the papers that we discussed today. So I'll be linking those links in the comment section or in the description section, so that people who are interested, they can check out. And I'll also I'll leave a link to your Twitter account, so that I think you're pretty active over there, publishing some of the works. And like you said, that's the easiest way people can be updated to some of the research works that people publish. So I'll be linking that. But apart from that, I hope this was useful for people who are listening and learning more about your work, and especially the idea of theory of machine learning. And I hope they get inspired, they get interested into this topic, and this field progresses. But apart from that, thanks a lot for doing this. I know you had a bad health last week, so thanks a lot for still putting up. And yeah, hope this was useful.
Yeah, thank you for having me. I very much enjoyed chatting with you.
Thank
Thanks.
you.
Bye.
Have a nice weekend. Bye bye.
You too. Bye.